speaker is Sepehr Nezami. He will tell us about error correction of quantum reference frame information, which is actually fresh out of archive tonight, like last night.
So hi, can you hear? Hello? Oh. So first, I would like to thank the organizers for giving me the opportunity to talk here. I'm going to present the work error correction of quantum reference frame information, which, as Benny mentioned, just came up last night, so it's pretty new. And this is a joint work with Patrick Hayden, my advisor, Sandy Popesco, and my friend Grant Salton, who is sitting there. So let me start with the motivation. So in this talk, I'm going to talk about the reference frame error correction and basically the reference frame information. And for us, reference frame information is kind of the information needed to specify a coordinate system in a space. Or as I may relax the condition, it's kind of any directional information in a space. So in the next few slides, I'll tell you that why is kind of different, why it's a different type of problem. So here, suppose consider a classical example. At this point, I don't need to talk about quantum information. Just the classical is fine. So suppose that we have Alice, and she wants to send a letter to Bob. It's type of kind of abstract information, so she can encode it in zeros and ones and sends everything in a series of bits to Bob. And this is quite trivial. Now suppose that Alice wants to perform a different task. Alice has a stick in her reference frame and wants to kind of send the information about the direction of the stick to Bob so that Bob can prepare a stick pointing in the exact same direction. And it still is kind of a trivial problem because Alice can measure x, y, and z coordinates of her stick and just encodes them into bits and send them all to Bob. So nothing interesting yet. But now I change the problem. Suppose that we have Alice here and Bob, but they do not share a reference frame, which means that Alice and Bob are oriented in an unknown way in the space. Alice does not know the reference frame of Bob, and Bob has no idea about the reference frame of Alice. Now the question, and they still want to perform the same task. Alice has a stick, and he wants to send the information about that stick to Bob so that Bob can prepare the arrow pointing at the exact same direction. So now as you can see that this task is not possible with just sending a bunch of zeros and ones, and Alice cannot say call Bob, tell him a series of bits, and so suddenly Bob can create a stick pointing in the exact same direction. So in that sense, you cannot send this information about this direction to Bob with just a series of bits. But does it mean that this information cannot be sent? Well, not entirely, because Alice can send the whole physical object to Bob. So somehow this type of information can be sent if you allow just transmission of kind of physical objects, but not a series of bits. And I will elaborate more on this topic, and I'll be more precise, but this is just what we need for the motivation. So as I mentioned, this type of reference frame information is different from the abstract information, which can be presented by a set of bits, or in the quantum case, qubits. And there is a large literature studying this type of information in the quantum case, and it's associated with interesting quantum phenomena. And one example of that is that suppose that you want to send Alice wants to send some direction to Bob. And one way to do that is that Alice prepares two spins pointing in the exact same direction. The other way can be just preparing a spin in an anti-parallel way. And it happened to be the case that sending anti-parallel spins transmits the information about the direction that Alice wants to send in a better way and with a better precision. This is not what I'm going to talk about, but it's just an example of interesting things that can happen with the quantum reference frame information. So this is one part of my talk. It's the reference frame information. And the other one is this quantum error correction. I don't need to motivate that why quantum error correction is interesting because we are in QEC. So I won't do that. And basically my talk will be a studying of the quantum error correction for the reference frame information. And so far my talk, this topic looks kind of orthogonal to what has been talked about in the last few days, but it will get closer as I will go on. So don't worry. And here is the outline of the talk. I will talk about the reference frame information, or more generally, I will use the term physical information to somehow, mainly to indicate that I'm going to talk about something very more general than just the reference frame information. But I will define what I mean. And then, the next step, I will talk about the error correction of reference frame of physical information. I will define the task and mention and say that what I exactly mean by the error correction of physical information. Then I will go ahead and define a totally equivalent way of performing this task, of equivalent formulation of the problem. If the problem is that is it possible to perform reference frame error correction, I define a notion which is covariant quantum error correction, and I say that these two problems, 2 and 3, are totally equivalent. By covariant quantum error correction, I mean the type of error encoding so that the encoder does not require to have a reference frame or coordinate system to encode the information. So it's kind of already reference frame free. But I will be more precise in defining what I mean by that. So, and in the next part, I will talk about the main result of our work, which is a no-go theorem. And if you look carefully in the original problem of reference frame information I just described, there are two coordinate systems, and they are related by some unknown rotation. And basically, this rotation group is a central object in this object in this type of problems. And we can organize these problems according to different groups. So I will prove the no-go theorem. And I will show that if the symmetry group of the problem is a Lie group, such as the rotation group, and all of the codes are finite dimensional codes, like spins or qubits, then the quantum error correction of physical information is not possible. So it's just totally unlike the usual case. And then I will mention some related problems. Having this no-go theorem, we'll look at the conditions of this no-go theorem, which is saying that it should be a Lie group. If you have a Lie group, and if you have a finite dimensional code, then error correction is not possible. So I want to make constructions when I relax each one of these conditions. Say I want to say that if my group is not a Lie group, can I make a code? And I give you constructions, explicit constructions, when I have a finite group and a finite dimensional code. And then I relax the other conditions. I construct error correction schemes when I have a Lie group and an infinite dimensional code. So this is kind of saying that we cannot, these conditions of this group are kind of necessary. You cannot make it stronger in that sense. And then I will talk about the random codes. I'm going a bit faster than the usual. So now let's go back to the physical information. Remember the setup. We have Alice here and we have Bob here. They're oriented in some unknown, with some unknown relative rotation in space. And Alice wants to send the direction of a stick to Bob. And as I mentioned, it's not possible to do that with a series of bits, but it's in principle possible. What Alice can do is that she can prepare a stick, she can prepare a gyroscope rotating in the exact same direction and send the gyroscope directly to Bob. And in this way, Bob can receive the information and can prepare a stick pointing in the same direction. So here comes the definitions. So I want to define the physical information and what I mean by physical information, and I want to define it in contrast to the abstract quantum information, the usual qubits that we use. And I define the abstract quantum information to be the information that's independent of physical implementation of the system I use for storing the information. On the other side, physical information is connected and is closely related to the physical properties of the system. And what I mean by that is actually, so there is one way that I know to attach physical properties to a system, and that's by defining action of some symmetry group on the data. And I don't know if it's the only way to do that, but this is basically the way that we define physical information here. So it's the kind of information, but I have some symmetry group that acts on my data. So, and the subject of our talk going to be studying the error correction of physical quantum information. And I have to mention that there has been previous important works in this topic. One is this clock synchronization, and of course, reference frame quantum information. And many of the topics just fit very nicely in the framework of resource theory of asymmetry. And yes, so then in the next slide, I will talk about what I exactly mean by error correction of reference frame information. So here I show this problem with an example. So I will use 1, 2, 3 encoding examples, and I use spins or qubits. But I use the term spin because I want to actually emphasize that some rotation group acts on my degrees of freedom. And I also talk about the erasure code, but this being erasure code is not just for this example. I will just talk about erasure codes in all of the talk. So this task has 6 steps. The first 4 are just actual error correction, and the last 2 are verifications. So now I start with Alice, same setup, and Bob, oriented in some weird way in space. And Alice has a spin, and the orientation of the spin is unknown to Alice because she should be able to encode anything. And we have this encoding. So step 1, Alice encodes her spin into 3 spins. And just to mention again, I'm talking about the reference frame. I'm just defining the process of reference frame error correction. I'm defining the success in that task. So the next step 2, one of the errors destroys one of my spins. So for up to here, I had 3 spins, encoded spins, and now I have 2 spins. And the next step 3, Bob receives the spins. But he receives the spins up to some rotation and the relative rotation is unknown to Bob because he's oriented with, they don't know each other's reference frame. And the goal is that Bob, although he doesn't know the rotation of this, although he doesn't know the exact rotation, he should be able to recover the spin, as you see here, pointing exact same direction as Alice's spin. And maybe some of the audience can't see this picture, I'm sorry. And the last 2 steps are the verifications. So Bob sends that spin through a hypothetical perfect channel to Alice, and then Alice compares that to the original spin and says, yes, this is pointing same direction, and they're all happy. So now I define the task, and I want to define the equivalent problem of reference frame error correction. So please keep in mind that now I'm going to discuss this problem a bit in more details, and we assume that the error correction, reference frame error correction, is possible. So let's study the problem. Suppose that Alice has the input state rho, and Bob, in his reference frame, sees the state rho tilde, which is a rotated version of rho. And of course, this UR acts on rho. U is the representation of this rotation group, and this R is the rotation matrix relating these 2 reference frames. And about the encoded state is this 3 spin state. Alice again sees the rho encoded, and Bob sees the rho tilde, which is a rotated version of rho encoded. But the rotation group acts by this tensor, this tensor product weight. It acts by the U tensor 3, because we have 3 spins, and the rotation group acts on each one individually. And now in the last step, I go to the encoding map. Suppose that the encoding map is simply just E naught rho as seen in Alice's frame. So what is the encoding map in Bob's frame? We have a state rho in the encoding. But Bob knows the state rho tilde. So he should rotate it back to rho, as you see here, using the first line, and then encodes this map. So this is Alice's encoding. But then this map should be the encoding in Alice's frame. So he should be rotated back using the second line to Bob's frame. So this whole rotated map is the encoding as seen by Alice. But the point is that now, this is the encoding as seen by Bob. But now the problem is that R is unknown to Bob. So he should be able to recover the information out of this channel, although he doesn't know the R. So just repeating the same thing. And yes, so this is the rotated channel. And now, so this means that Bob has a fixed encoding independent of R that can recover a ratio of one of the errors out of this channel for every R. This also means that if we average over all of these channels and define this channel E of rho, then Bob can still also recover this specific integrated channel. So this is also a correctable channel for Bob because he can correct for every R and just say an average over these different channels. And even at this stage, you can see that this channel is doesn't know any coordinate system because it's already integrated. We are already integrating over all possible coordinate systems. So in that sense, this is a covariant. But in the next slide, I will define exactly what I mean by the covariance. So covariance is defined with respect to a group G and a representation U, and this thing. So if I have a channel, I define starting from here up to here is the rotated channel, is the definition of rotated channel. I don't know why I put tensor products here and not the tensor buffer, but this is the same rotated channel. And the condition is that for every R, this is equal to the original channel. So this is the definition of covariance. So far I established that if we have succeeded in the reference frame correction, we also succeed in covariant correction with this one. And the opposite is also simple to prove because you say that I have a covariant channel, so it doesn't know in a reference frame. So it actually doesn't matter that they don't know each other's reference frame. Alice can encode it in any reference frame. So these two problems are basically equivalent. And I have to mention that this type of channels are basically the objects of study in the resource of asymmetry. So this talk can very well fit in that framework. And now my question is that does there exist a covariant encoding channel that can correct a ratio of a single mode? A 1-to-n encoding can correct a ratio of a single mode. And as we will see that this answer will depend on the size of the code and the group. So this is the main slide of one of the main slides of the talk. So here we prove a no-row theorem. We show that there is no perfect covariant error correcting. No perfect covariant error correcting schemes can be implemented. So if we require that the error correction is perfect, and if we assume that the group G is a Lie group, and also the coded space is finite dimensional, then there is no covariant error correction. And this already applies to the original reference frame error correction problem, because there we have this rotation group, which is a continuous group. And the coded space is finite dimensional. We are encoding spins. So this already gives you an answer that for the original reference frame error correction, when we have Alice and Bob's, this task is impossible to achieve. And I have to mention that this proof is basically based on the infinitesimal generators, and proof is relatively simple. And Now, in the next slide, I'm going to talk about the related problems. A while ago, when I was talking to Benny, dear chair, he said that, oh, this is kind of a Ising-Knowles theorem. So it's a version of that. So I will talk about these related problems. So so the Ising-Knowles theorem, as you all know, is the problem that is saying that there is no erasure correcting code in a way that it's not possible to have erasure correcting code in a way that all of the gates can be implemented transversally. And you can see that why this is a covariant you can see that why this is a covariant condition, because the fact that we can implement the transversal gates universally, it means that suppose that this is my logical space, this is my logical modes, and these are the physical qubits, the physical modes. And the encoding of this logical space to the physical space is happened with this encoding channel. And I want to say that this encoding isometry is covariant. Why is that? Because we know that any unitary can be implemented in the logical space. And the fact that this unitary can be implemented transversally means that there are a set of tensor product unitary representation of the same unitary group on the physical modes that can do the same job. So, and you can see that at this level, this follows from our Norroth theorem. For the specific case when the G is a full unitary group, it's not a specific SO3 or any representation, it's a full unitary group. And the encoding channel is actually just an isometry. And I have to mention the Ising-Knowles has, of course, more parts into it. It just talks about different components of the unitary group, but yeah. And then the other example is just that I will not have time, I don't have time to talk in details about is just invariant perfect tensors. And it was just recently was a conjecture that these objects do not exist for a specific range, and you can see that existence of invariant perfect tensors will mean that you have covariant error correction schemes for some range that is just because there's no covariant error correction schemes. It also says that there's no invariant perfect tensors. And I'm sorry for the very short description of this fact. So then, yes. So now I talked about the no-go theorem. I will talk about the relaxing the conditions and the ways that we can circumvent the no-go theorem. So one way is that just relaxing the condition that I have a Lie group. So suppose that I just have a finite group instead of a Lie group. And I want to give you explicit constructions of a finite group when you have a finite group and you can encode it in a finite dimensional Hilbert space. So I say that it's possible for any finite group G, we find examples of perfect covariant error correcting schemes. And this looks very general because it works for every G, but it comes at a price, and that is that I choose the representation, and I choose the representation that works well for me. So first, remember that every group is a subgroup of every finite group is a subgroup of a permutation group. So it's sufficient to study the problem just for the permutation group. And for example, for simplicity, I assume that the permutation group is S3, just a permutation group on 3 elements. So that's the time. And yes. So the construction is the following. Suppose that you choose your favorite non-covariant encoding. Just we can imagine each one of these forks is a 1, 2, 3 encoding. Maybe the Q3 codes that Dan Harlow mentioned. So any one of these forks is an encoding, non-covariant. And if I have permutation group on n elements, I put n replicas of this code. So I have tensor product of n codes. Here, I have tensor product of 3 of these forks, 3 codes, because I'm trying to talk about just S3, the permutation on 3 elements. And I define the action of the group to be the one that permutes these different replicas. So, and you can see that this encoding goes vertically, and it just commutes with the action of the with the action of this permutation group, we just permute these different replicas. And you can see that, for example, in this picture, if we first apply the transposition of the first two elements, if we first two replicas, and then they perform the encoding, I get this construction. And if I first encode and then do the transposition, I get the right-hand side. So and you can compare this wiring of this bunch of forks, and you see that these two codes are the same. And this is the same covariance condition. So this is a code, but code has a relatively bad property that the dimensions can grow exponentially with the size of the group. And I will come back to this point later when I talk about the random codes to give you smaller codes. But for now. So now I talked about the finite group and the finite dimensional coded space. Next construction I give is the construction of infinite, when I have an arbitrary group, but I allow infinite dimensional codes. And it happens to be the case that this is actually very simple and trivial. And so far, I mostly focused on the covariant error correction version of the problem. But it's very interesting to note that sometimes the covariant error correction picture works simpler. Sometimes the original reference frame error correction picture works simpler. And this happened to be the case that for this type of code, this problem is much simpler in the original reference frame error correction. So I tell you how we can perform error correction of an arbitrary group G if you have access to infinite dimensional code. So start from here. Alice has a spin. And again, she uses her favorite encoding, non-covariant encoding, whatever she uses. But she supplements her encoded qubits with two big infinite dimensional classical indicators of the reference frame. So you can imagine that Alice is sending two big systems of infinite dimensional, two big systems of classical gyroscopes which totally determine the reference frame of Alice. And I have to send two because of this condition that I may lose one of the modes. It might be the reference frame that I lose. So then I send all this information, and Bob receives this information. And then what Bob does is that he looks at this reference frame indicators and totally reads the reference frame of Alice with infinite precision, because this classical system is infinite dimensional. And what Bob does is that Bob rotates himself to Alice's frame because he already knows this frame. And it's kind of cheating, of course. And then Bob recovers the state. So this was one solution. And now it's interesting to look at the same problem in the covariant error correction picture. Yes. And it's happened to be the case that this is slightly more complicated in the covariant error correction picture. And what we have to do is suppose that Alice uses you have your favorite non-covariant code. I shouldn't talk about Alice because it's just like I don't have this picture anymore. So I have this E0 code, and I define the rotated version of this channel. And what I do is that I integrate over G, over all rotations of this rotated channel, but I tensor product it with two registers. And these two registers each one has a basis for each element of the rotation group, or my group. And it can be, for example, it can be the regular representation of the group. And what the decoder can do is I can just look at these two registers, because there is a basis is classical. He can read say, the group G, and then rotate the channel back to the original frame, and then recover the state. And something I want to emphasize here is that here this channel is not an isometry. So this is actually important that we have this no-go theorem for generic channels. And now you might be upset and depressed that this was kind of cheating. It was really trivial construction. So in the next slide, I'm going to give you a bit more non-trivial, although formal construction for a specific code. Suppose that you have a specific, I will define a specific example of a U1 covariant code. now I choose my group, my symmetry group to be just a U1, a simple phases. And I define a 1, 2, 3 mode encoding. And in this part, I will not send the reference frame anymore. So it's kind of more non-trivial. And what I do is that I choose my local Hilbert spaces to be finite dimensional, to be infinite dimensional, and there are actually a space of functions on a circle. So it's kind of a regular representation of the U1 group again. And we can solve the error correction condition. The solution exists, and I have this type of maps. X to this superposition. And the X are integers, which are the Fourier basis, which are this Fourier basis elements, which, yes, it's written in the Fourier basis. So this X is integer because this space of functions, this circle is compactified. I get just integers. So this is one version of the map. Yes, I guess I'm going too fast. Yes. And so now I talked about this specific example. Then I go back to the usual finite group and finite codes. And now I'm going to give you better parameters for a smaller physical Hilbert space. So what I do here is that, so if you remember previously, the code was, the size of the code, the size of Hilbert space can be exponential in the size of the group. And now I'm going to give you a kind of construction that each local Hilbert space is equal to, is qubit when D is actually order of the group. So somehow the Hilbert spaces, local Hilbert spaces are this regular representation of my finite group. And what I do is I choose random codes. So I look at the set of isometries that map one mode to n mode, one qubit to n qubit, and the finite group acts by a regular representation on each one of these qubits. And then I choose a totally random isometry in the space of this covariant codes. And what we can show is that for n equal to more than 4 number of output qubits, so if we have 1 qubit to 5 qubits, 1 qubit to 6 qubit, then in the limit of large dimension, the order group, large dimension, which dimension is equal to group order, these are pretty good encodings. So we can prove, for this result, you can work a bit harder than the previous ones. And what you can show is that the worst case fidelity of recovery is very close to 1. It's exponentially close to 1 in this limit when we have more than 4 output nodes and the group order is large. I'm sorry for this. I apologize for this bad equation. But yes, but you can see that in the limit of large D, and if n, the number of output is 4 than 4, this fidelity of recovery, worst case fidelity of recovery is very close to 1 by a big exponential factor, and it's going to be doubly exponential in number of output modes. So this is a version of approximate code. And so with this, I go to my conclusion. So what we did here, that we studied the quantum error correction of reference frame information, and we divided this problem into actually 3 cases. We show that if the group is a Lie group and we have a finite group, the reference frame error correction is not possible to be done perfectly. So this was a no-go theorem. Then we studied the case of the finite code and the finite group, and we showed that it's possible. And then I studied the just arbitrary group, but I allowed for infinite code, and I showed that it's also perfectly possible. And this finite group infinite code is kind of trivial, because if you can do it with infinite code, you can also do it with finite code. So this is just, I didn't talk about, but it's there. And I finished my talk with a couple of open questions. So one is that, of course, what is the approximate version of this error correction of reference frame? What happens if I allow some error tolerance? And what I can say about this problem. And the other one is that is there any explicit relation between the size of the group and the dimension of the code? We show that if the group is infinite dimensional, you cannot encode it into finite dimensional. If a group is infinite dimensional, you cannot encode it in finite dimensional codes. And we show that if somehow the cardinality of a code and the group order match, then we can perform error correction. So the question is that, is it possible to find explicit relations between group size and the dimension of Hilbert space? And lastly, about this U1 code, can we make it more precise? Can it be implemented? Or are there interesting other infinite dimensional codes for different groups? Can we extend it to the full unitary group of, say, SU2 or other cases? And with this one, I'm going to finish my talk. Thank you.
So any questions?
I have two questions. One is like technical. So it's suppose instead of like Bob having no knowledge of his reference frame relative to Alice, suppose like he knows it's in some solid angle, which may be small. So like he has some uncertainty, but not complete uncertainty.
So you're saying that it's a rotation just around the x-axis?
Yeah, or but for some limited angle.
Or for some limited
Like
angle.
in other words, Bob knows he's like kind of a little tilted, but not like completely tilted.
I would say the same proof should work. I think. I have to check that. But because basically what matters for our proof is the infinitesimal or generators of the rotation. So it's basically what matters is just the small rotations around this point. So I think then the result applies to that case, but I have to check it.
Second question is if the rotation group emerges at low energy from a discrete symmetry group, like say on a lattice, does this imply that you can, in some sense, approximately correct it using the discrete?
Well, I think the answer should be yes, because first of all, I mean, you can imagine having your symmetry group is growing. So as you look at the lattice, I mean, it's not. I mean, I think it's possible. It's probably even possible. You can probably do random codes. Although I should mention that the random codes actually work perfectly for the regular representation, but not the usual representations. But I think you should be able to get some approximate result, some approximate version of these results. Although I'm not quite sure that this type of statements are very much robust to the size of the group. Well, yeah, I mean, for example, if you can go to the infinite, the limit of having the rotations, having the full rotational group in the limit of, say, suppose that you have ZP rotations, and the P gets larger, then for each ZP you can find the code, or say use this U1 code, mod P, and in that limit you can probably say that as P goes to infinity, my group goes to the U1 group, and this isometry is not in a strict sense go to a fixed isometry, but somehow formally they go to the same isometry. But yeah, that's a very interesting question.
Any other question?
Thanks for the talk. Do you think a similar result can hold if the communication channel is not unitary? Like, for instance, if the metric is time dependent?
If the so the result was for arbitrary covariant or arbitrary channels. So somehow I don't require it to be a unitary, so it can be in any channel. So it already applies, but maybe you're talking about something deeper.
No, actually, yes.
Okay.
Yeah, I got my answer. Thanks.
Any other question? Actually, I have two questions. So, a very quick question. So, about this construction of the U1 case, random. So, basically, is it so in this 1, 2, 3 code, I prepare like 4-party state with this charge neutral state randomly, and then does
Right.
it work? Basically, that's how it works.
Yes.
I see. And then other question is more kind of philosophical, but I feel that these things may be related to quantum gravity and so on. Then I think this, like whether global symmetry can exist on bulk and so on are very interesting questions. And then I think this is a question about global symmetry of the state or code, right? So is there any implication of your result?
Well, the global.
Like
I would say that, I mean, you might be able to interpret it in terms of tensor networks. So suppose that you have your tensor network construction and tensor network construction, and you want to impose this, you want to impose some physical, I'm not sure I'm answering the exact question, but it's
I mean, my question is not well defined, so.
So just imagine that your question is the one that I'm answering to. So, yeah, I think you can imagine imposing some kind of symmetry. I mean, if you have some physical symmetry in your system, you might want to impose it at the tensor network level. So, for example, when people talk about this loop quantum gravity, they have these constructions which are similar to tensor networks, but they have SU2 symmetry. I mean, that was actually why people define these invariant perfect tensors. And then the question is, for example, if you want to say that, oh, I want to keep my symmetry in the tensor network level or just some kind of a state level, and then I still want to perform this entanglement bridge reconstructions perfectly, then this result will say that, oh, no, it's not possible. But I guess there are good physical reasons to imagine that you want to impose some kind of symmetry at this level, for example, maybe coming from loop quantum gravity or something else.
Okay.
But was it satisfying somehow?
Half.
Okay.
Anyway, thank you. Okay, so I think it's time to thank you.